So, ladies and gentlemen, it's a pleasure to ask Professor Singh from Tata Institute, Mumbai, to talk on gravitational phenomena.
Thank you. I hope you can hear me well. My thanks to my collaborators who made this research program possible. Let me start by quoting this following remark by Ed Witten: "Spacetime vector bundles for muons, dynamics, our knowledge of physics." He says, if one wants to summarize our knowledge of physics in the briefest possible terms, there are three really fundamental observations. Spacetime is a pseudo-Riemannian manifold M, endowed with a metric tensor and governed by geometrical laws. Over M is a vector bundle X with a non-abelian gauge group G. Correspond are sections of S plus cross VR, some S minus cross VR bar. R and R bar are not isomorphic. Their failure to be isomorphic explains why the light fermions are light and presumably has its origins in a representation difference delta in some underlying theory. All of this must be supplemented with the understanding that the geometrical laws obeyed by the metric tensor, the gauge fields, and the fermions are to be interpreted in quantum mechanical terms. Let's try in this project to bring these three remarks under one unified fold by using Adler's theory of trace dynamics, octonions as coordinate systems. So what do we need as ingredients for unification? What do we need as ingredients? Sorry, this is moving. No, three. What do we need as ingredients for unification? A new dynamics, a new Lagrangian, a new coordinate system, and the old symmetry E8 cross E8 which we revisit. Adler's pre-quantum theory of trace dynamics is a matrix-valued Lagrangian dynamics that we work with. Octonions as a non-commutative space-time manifold instead of R4. The Chomsky-Cohn spectral action principle used the Dirac operator instead of the metric as a dynamical variable for general relativity. Exceptional Lie groups for symmetry, including E8, and Clifford algebras for making spinors from octonionic maps so as to define elementary particles. A new concept of time unique to Cohn's non-commutative geometry, derived from the so-called Tomita-Takisake theory, and evolution will be described in terms of Cohn's time, not coordinate time. And what is very important to remember is that there is no change in energy scale vis-a-vis Witten's remarks, our knowledge of physics. Whatever is said there, staying at the same energy scale, we want to recast in a new language which we think is beneficial. So in a nutshell, in this diagram, once again the ingredients for unification are shown. At the upper level is the observed world, the 4D Minkowski space-time curved by gravitation, on which fermions and standard model gauge fields live. What is being advertised is, let us take the square root of this Minkowski space-time, just as we take the Dirac of the square root of the Klein-Gordon to arrive at the Dirac equation, and that does not involve any change of energy scale. Let us take the square root of 4D Minkowski space-time. That will give us a quaternionic space-time, or what we can also relate to Penrose's twistor space. Over there, let's go from complex numbers to quaternions onwards to octonions, and what we find is that we now have an equivalent of a 10-dimensional Minkowski space-time. If you square the octonionic space, you'll get the 10D SO19 Lorentz group familiar from string theory, but we are not going to do string theory. The standard model gauge fields and pre-gravitation are expressed as geometry of this square rooted octonionic space, more precisely the complex bioctonionic space with the symmetry E8 cross E8, and fermions at all energy scales actually live in this level. Fermions should be described on the square rooted or a spinor spacetime, and then critical entanglement between fermionic degrees of freedom can give rise to emergence, where classical degrees of freedom live in 4D spacetime, and although the quantum fields are living here on this octonionic space, they can be projected onto the 4D classical spacetime so as to recover QFT on spacetime in the conventional sense. Just to remind again, in taking this square root, there is no change in energy scale, and it's just a new formalism, a new language. Okay, from Newtonian dynamics to Adler's trace dynamics. Yeah. So this is the action for a free particle in Newtonian mechanics. It is the time integral of the kinetic energy, which is the Lagrangian. What Adler says is, let's replace real number dynamical variables by matrices. So Q goes to bold Q, which is a matrix. And let us work with the same Lagrangian. So now we have Adler's matrix valued Lagrangian dynamics. The Lagrangian has become a polynomial in matrices. Let's take its matrix trace. That trace Lagrangian is a scalar, and do its time integral to get the action, or if you want to work with fields in the continuum, do a space-time volume integral. What have we gained? There is a novel conserved charge which emerges in this matrix dynamics as a consequence of a global unitary invariance of the trace Lagrangian and the trace Hamiltonian. A novel charge shown here by the symbol C tilde is the sum over bosonic degrees of freedom of the commutator QB minus the sum over the fermionic degrees of freedom of the anti-commutator QFPF. This is what leads to this matrix value Lagrangian dynamics being a pre-quantum theory. It's even more quantum than quantum in the sense that the individual commutators are determined by their dynamics. They are not fixed to the Heisenberg algebra IH bar, but their sum remains constant. This carries within itself the germs of quantum theory, which is emergent. Trace dynamics to quantum field theory as an emergent phenomenon. Assume trace dynamics to hold at some time resolution tau Planck, say some time interval higher than what has been currently observed in the lab, let's say Planck time or anything about it, electroweak energy scale. So what we have is a Lorentz invariant matrix valued Lagrangian/Hamiltonian dynamics. We ask, what is the emergent dynamics at time resolution tau much greater than tau Planck? We are not observing the fine-grained system but the coarse-grained system. Statistical thermodynamics is then used to show that the novel charge just introduced gets equipartition, and since it was a constant to begin with, all the equipartition components are constant, and that those are defined to be IH bar. That's how Planck's constant emerges in the dynamics. The Heisenberg equations of motion are recovered as coarse-grained averages of the underlying Hamilton's equations of motion, and quantum field theory, Adler shows, emerges as a thermodynamic equilibrium approximation of trace dynamics. And it turns out if there are fluctuations about equilibrium, and if those fluctuations are large enough, well, the system moves away from equilibrium, and that is a quantum to classical transition. Classical systems emerge in this theory if the imaginary part of the Hamiltonian becomes large enough to force the system away from equilibrium. Okay. Trace dynamics has a very interesting property. You are probably familiar with supraquantum correlations discovered by Popescu and Rolnick, who showed that in the CHS inequality, the condition of relativistic causality and non-locality permits non-local correlations stronger than those allowed by quantum theory. The quantum bound is 2√2, And we recently showed that this region, which was up till now not understood, supra-quantum correlations are actually what are allowed by trace dynamics when the novel charge is not equipartition. In other words, if you have a pre-quantum theory but you don't have the Heisenberg algebra, you will recover supra-quantum correlations, suggesting that quantum mechanics is actually approximate and not exact. Okay, so we have the dynamics, we have Adler's trace dynamics. Now we want to ask, what is the Lagrangian we want to work with? We don't want to work with a metric. It is too different from Yang-Mills fields. However, there is this famous theorem, the spectral action theorem in Cohn's non-commutative geometry, according to which the Einstein-Hilbert action in a heat kernel, in a truncated heat kernel expansion, the regularized Dirac operator d square is actually related to the Einstein-Hilbert action. In other words, given a Riemannian geometry, construct the Dirac operator on it, then trace LP square d square is actually proportional up to a coefficient to the Einstein-Hilbert action on the space-time manifold. In other words, the Einstein-Hilbert action can be written as in a spectral form, as the sum of the squares of the eigenvalues of the Dirac operator. And Landy and Rovelli showed that the Dirac operator can equally serve as dynamical variables for general relativity. The eigenvalues of the so lambda i's have the same status as that of the metric on the manifold. So it is these lambda i's which we are going to raise to matrices in the sense of Adler, which matrices, the varying Dirac operator of which they were eigenvalues. So each lambda I is made into a matrix slash operator lambda I hat, which is used to define this configuration variable QB, whose Cohn's time is unique to a non-commutative geometry. The Cohn's time derivative of QB is this matrix valued Dirac eigenvalue, which has now been. So you see, for each eigenvalue you get a Dirac operator, and the universe is fundamentally made up of many atoms of space-time, each atom being the quantized Dirac eigenvalue, so to say, having an associated velocity operator QB dot. And what is the Lagrangian for the ith degree of freedom? Is nothing but trace QBI dot square integrated over Cohn's time. And if you now sum over all the eigenvalues, you will get the quantized version of Einstein's general relativity by sigma I trace, etc. And to recover the classical limit, each eigenvalue operator is sent back to an eigenvalue, and then you sum over all the eigenvalues and you again recover general relativity. In this we can introduce fermions so that this becomes an atom of space-time matter, which is essentially really like the string of string theory. And we can also include Yang-Mills fields. Please have a look at this. Beta 1 and beta 2 are two unequal Grassmann numbers introduced to make the Lagrangian bosonic and then onto a scalar. LP is L is the fundamental length scale of this two brane. It's a two brane because beta 1 and beta 2 are not equal to each other. So this is really the expression of the Einstein general relativity including matter in terms of the Dirac operator on the geometry, which is now non-commutative. To include Yang-Mills gauge fields, introduce this Yang-Mills coupling constant alpha, and the fields are introduced as matrices precisely in the same spirit as in relativistic quantum mechanics. P goes to P plus EA is how you introduce a vector potential. So here P is like QB dot. QB dot goes to QB dot plus QB times alpha. So it's the same spirit. So this is our fundamental Lagrangian for one atom of space-time matter, just here. Okay. Okay, the fundamental Lagrangian for one atom of space-time matter, and the whole universe is made up of many, many copies of such atoms. The claim is that one can recover from critical entanglement the classical universe from here, and the claim also is, it's a very tall order, but it seems true, we are working on it. This contains all of the standard model plus 3 generations of quarks and leptons, standard model gauge fields, and general relativity. I try to build that case. So in that sense, this is stringy, but you will see what the differences are. So we have the dynamics, trace dynamics, we have the Lagrangian, now the coordinate system. We wanted to work with the square root of Minkowski spacetime, but instead of complex numbers and quaternions, if we go to a larger space of the octonions, they are rich enough to allow the standard model. So Witten's vector bundle plus manifold in the Kaluza-Klein sense will now be replaced by an octonionic space. Algebra automorphisms take the place of diffeomorphisms and gauge transformations, and permit unification, again emphasizing there has been no change in energy scale in going from Witten's language to here. Division algebras, real numbers, complex numbers, quaternions and octonions have been investigated by many researchers for their connection with the particle physics. The quaternions you are familiar with. And interestingly, the Dirac operator is nothing but the gradient operator on quaternionic space, and as what we are working now in that Lagrangian is the Dirac operator on octonionic space. The Lorentz groups in 4, 6, and 10 dimensions bear a close relation through the division algebras shown here. And what is the sense of the physics? How is curvature? How are fields introduced? They are introduced as matrix-valued components of the octonionic directions. Earlier, in general relativity, curvature is introduced by replacing eta mu nu by g mu nu. Here, gauge fields, fermions, and gravity are introduced by introducing these matrix-valued coefficients of the octonionic directions. In other words, geometry and curvature is being introduced at the square root level. So now you can take the square of this and that will be equivalent to general relativity. Okay, so we have the Lagrangian, the coordinate system, and the dynamics, and lastly we want to introduce the symmetry group. Before that, octonions, Clifford algebras, and elementary particles have a very close relation. For example, complex quaternions can be used to define the Clifford algebra CL2 as well as CL3, which gives rise to left-handed and right-handed Weyl spinors obeying the symmetry SL2C, the Lorentz algebra. Similarly, complex octonions can be used to construct one generation of quarks and leptons because the smallest exceptional Lie group G2 contains within itself SU3, which allows us to make the Clifford algebra CL6 and CL7, and Fury showed and also beautiful work on CL6 by Christie, who's here. And charge quantization is shown as a consequence of this procedure, and one generation of the unbroken substandard model symmetry SU3 color across U1 EM can be described using CL6. Now, how about 3 generations, electrovy and gravity? So this is rewriting in the same Lagrangian once again in a more compacted notation, mainly to remind you of a very important point, that coupling constants arise as a result of a left-right symmetry breaking identified with electroweak symmetry breaking. QB dot has to do with the gravity, QF dot has to do with right chiral fermions, QF with left chiral fermions, and QB with standard model gauge fields. 5 plus 5?
10 minutes or 10.
Okay, 10, very good. Okay. So we will assume that this Lagrangian has E8 cross E8 symmetry. Why did we do that? Because it allows a very interesting branching Okay. E8 cross E8 unification of the standard model and pre-gravitation using the Lagrangian just showed. We found this following interesting branching of E8 cross E8, SU3 color, SU2 left cross U1 hypercharge, then a new sector, SU3 grav cross SU2 right-handed. This SU2 right-handed will become general relativity. U1 grav is a new degree of freedom, usually called the dark photon, and SU3 grav is what seems to give a large-scale conformal gravity modifications to general relativity. The 248 sum 1 248 of E8 cross E8 is broken into two separate E8s. The first E8 branches into SU3 Euclidean space cross E6. The second E8 branches into SU3 space-time cross E6. So there is a SO19 here, there is a SO10 here. So there you see the picture of Wigton's vector bundle plus the manifold. The manifold is coming here now, 10-dimensional space-time manifold, and the vector bundle, the information is carried by this Euclidean space SO10. The E6 breaks into three SU3s. The first E6 is identified as SU3 left-handed generation, SU3 color, SU2 left, U1 hypercharged standard model. The second E6 very fundamentally seems to have to do with gravity. SU3, three right-handed generations, SU3 grav as a new gauge degree of freedom, SU2R which identifies with general relativity, and U1 grav, the dark photon. We introduced a new quantum number, the square root of mass. The left-handed chiral fermions have associated U1 quantum number which is electric charge. They are charged eigenstates. The right-handed chiral fermions have a U1 charge with the square root of mass. They are mass eigenstates. Electric charge and square root mass are emergent after this left-right symmetry breaking, which in this theory is also the electroweak symmetry break. So, in this picture, we have a Lagrangian for the standard model defined on this bi-octonionic space, obeying the laws of trace dynamics, and we get the three generations of quarks and leptons, 12 gauge bosons, 4 Higgs boson degrees of freedom, and an additional gravity sector. So in that sense, it seems like there is a unification in this picture. What's the difference from string theory? We are working with octonionic space. Fermions are defined in octonions, not on SO19, but on the square root of SO19, which is the octonionic space. And because coupling constants arise as a consequence of symmetry breaking, the coupling constants are actually determined by the octonionic algebra. The alpha, the Yang-Mills coupling is nothing but the relative weight of the left and right-handed fermions that allows us to calculate at least some of the constants. The low energy fine structure constant, we claim the basic formula for it, which agrees fairly well with the experimental value. We have a derivation of mass ratios of quarks and charged leptons. We believe we have at least some understanding, say, of why the muon is 200 times heavier than the electron. Those numbers are given by these ratios derived from theory. Some estimate of the weak mixing angle, more work is needed, and almost done. The left-right symmetry breaking gives rise to the emergence of classical space-time and gravitation, because critical entanglement amongst fermions leads to the quantum to classical transition and emergence of 4D classical closed space-time, SU2L cross SU2R break. The principle is that classical systems descend from 10D to 4D in the quantum to classical transition, like shown in this picture, whereas quantum systems are always living in some space of E8 cross E8, even in this room. An electron in flight is not in 4D space-time, it is in a larger group space, and there seems to be no contradiction to that. So we have compactification without compactification, and the same mechanism applies in the early universe. Here is a listing of some possible testable predictions. No smoking gun prediction. Free gravitation is mediated by spin 1 gauge bosons. The graviton, if it exists, is composite. So hopefully you can please quickly read through it. This is the last slide. Of course, much remains to be done. You can read it here, and the slide recording is available on my webpage. I will stop because I'd like to leave some time for discussion. Thank you.
We have 5 minutes. Who would like to ask a question?
Thank you for these interesting ideas. Do you have a cosmological constant in your
So
approach?
my understanding is that the cosmological constant in this theory is exactly 0, because I see the Hamiltonian having a structure of what is known as, the Bateman oscillator. The coupling of two harmonic oscillators is opposite signs of the energy, and that suggests a cancellation. What then is dark energy? As I said, the classical limit when we took of the gravitational theory, the trace square Dirac operator, you get, according to the Chomsky-Cohn spectral Lacan principle, you get general relativity, but when you get Yang-Mills field, that gets accompanied by conformal gravity plus other curvature corrections. This conformal gravity looks a lot like Mond and the relativistic Mond. So the idea is that, Adler's also talking, that dark energy is something to do maybe with this U1, or probably also with this conformal gravity at large scales. So there is at all epochs in cosmology a competition between conformal gravity and general relativity. In the first inflation, conformal gravity wins, classic quantum to classical transition takes place, compact objects start to form, general relativity wins. But at large distances where the gravity is weak, again conformal gravity seems to win over again. So the universe is always inflating, but being overpowered by GR at some epochs in its history. Is that okay?
Yes.
Interesting.
Thank you.
Okay. So, yes, please.
Hi, so just a quick question. You mentioned that you do a sort of square root of general relativity. There is an old paper by Claudio Teitelboim, I think the title is The Square Root of General Relativity, in which he mentions that essentially would lead, if I recall, to supergravity. But in your approach you don't have any supersymmetry, is that correct? Could you comment a little bit on that?
Supersymmetry not in the conventional sense of producing supersymmetric particle pairs, but if you see how the degrees of freedom QB, QN, QF arise here, you can always map one to the other. So it's like there are 32 gauge bosons, there are 96 fermions. So it's like a 1:3 map. So there is some correspondence, but we are not having new supersymmetric particles, and I would like to see this Teitelbaum paper. I don't know this, because when we take a square root, it's in a specific sense of working with the octonionic coordinate system. There's another sense in which you could take the square root and work with triads or tetrads. Yeah, is that what was there, you think? Non-commutativity in the square root space is very important.
Okay, well, very quickly then, Professor
Yes.
Yockel.
Was just a curiosity about the choice of the group.
Ah, very good, very
Because
good.
you started off by quoting Witten.
Yes.
I remember some time ago we had E8 as a ground unification group
Yes,
In
yes.
the early 2000s. Is that any relation?
Okay, the heterotic string in the 1980s became very popular. They had two symmetry groups, SO32 and E8 cross E8, a few important papers came out, but then this trouble of compactification of Calabi-Yau manifolds, issue of uniqueness came up. Okay, so my statement about string theory is, should not have constructed particles in E8 cross E8 by perturbing around Minkowski spacetime. I would say that's a mistake. You just need to take the square root of Minkowski, and the square root of 10-dimensional Minkowski spacetime is nothing but the octonionic space. And then you can very nicely construct fermions and bosons, and they all seem to fall in place. And I will never compactify. I will not do a Calabi-Yau manifold.
We'll talk about it.
No. There is a dynamical process, the quantum to classical transition, which brings originally 10D quantum systems down to 4D. The classical systems are living in 4D. There is no reason to say that quantum systems are living in 4D. They can have that little extra thickness of the order of the range of the strong and the weak. So the fiber bundle, the vector bundle, is a physical reality. It is a part of the higher dimensional space-time. Let's say the curves are climbing. Does that help?
Thank you. Yeah.
Thank you.
So thank you, Lena Stockman. Thank you very much.